Okay, so welcome back. We have these 3 tutorials we have the option to go through, but we'll just start with one and kind of take our time on it, and then the others will feel much more familiar as we go through those. I think my notebook is still downloading the packages, but even if you don't want to download those packages and be able to execute the cells on your own, the output is there, so we can step through the notebook and talk about each section so that it feels really familiar. But if it does run for you, then you can always execute the cells and get it to work yourself. Before we're kicking off for the first exercise, just wanted to go through and get close to recreating the graphic that was created in The Economist article. And before we dive into our own analysis of the data, just wanted to kind of point out some of the things that we talked about in the previous hour. So they have their title, and then they've made a horizontal legend to kind of fit in the space that's available, and they have the different descriptions associated with the different regions of the world. And so it's not set off to the side, they've chosen to put it horizontally up at the top of the graph. The X and Y labels, incredibly important, actually describe the variable and the units, or the way in which to interpret them. That was really, really, really important because the corruption perceptions index, the first time I saw one of the tutorials, the person had just left CPI. And in the United States, if you're following a census or labor statistics, CPI is the index of inflation. And so it was really confusing. What is that variable? And even more so, is 1 good on the index, or is 10 good? And so they put down in the section 10 is the least corrupt. So 10 is good on the x-axis, and y is more corrupt, 1. And then on the y-axis, 1 is the best. So going up is good. So up and to the right is good between the two. But without the extra labeling, even when I was going through the exercises the first time, it was kind of confusing because it wasn't labeled properly. And then they have a nice instance of kind of adding some call-outs to countries potentially of interest. And then they can talk about those. And what's really nice about that is maybe you have an interest in a different region of the world. And so you could associate the line call-outs to individual observations for the countries you care about. And then people's eyes are directed to the countries that you're interested in conveying. And then the final one is the different data sources listed down at the bottom. We talked about that annotation. Just making sure people can reproduce the plot that you created, or at least find the original resources. So we'll use those. Okay, so mine finally finished. It really does, for these set of packages, not all our packages, but for the ones we're taking, it takes about 10 minutes to download everything. The Economist data is in the GitHub repo, so you have access to it. You can see there's a column of different countries, the HDI, the Human Development Index rank, the Human Development Index value. The CPI is not inflation, it's the corruption index, and then the region of the world. And you can see in the data types listed at the top, like you would see in Python or some other R package, region is character, and we need that to be categorical factor so that we can label our data correctly. In this package, just like other programming languages, there's different ways to kind of initially view your data set. I'm just showing a couple options you have. With Glimpse, it's kind of listed out in row form, so that you can see each of your variables, and you get a sense of how many rows we have, 173 countries, and 6 columns of different variables in the data set. Just like the earlier cell, you can also run head to just get a look at the data, get a sense of what values are in each column. In this data set and some curated ones, you may know there are no missing values, but there's a whole topic on dealing with a data set in which you're less familiar, or you know there will be missing values, checking it, where they are, and then why they might be missing, and dealing with that ahead of time. Just like in any other programming language, having a sense of ability to do data type transformations. So this column of data was character, we're trying to make it factor, so we can use that factor capability in some of the plotting. And then we talked about, we're going into our analysis, do some initial exploratory EDA on each of the variables. We want to look at the relationship between HDI, the Human Development Index, and the Corruption Perception Index. This is kind of our initial bivariate plot, scatter plot, leading up to the final visualization. So within R, there's a built-in function called pairs, which will show pairwise relationships between different variables, and we pass in which variables we want to look. We can customize the circles. The shape is PCH and the size is CEX, make them a little smaller, and then we can color them by the hue for each category of the country, world. And so we're just using a hue palette that is categorical colors for different categories, different regions of the world. Since later on, we don't want to deal with the built-in colors, we want to be able to customize our colors, just getting a sense of how we can look at use the packages that we have available for seeing what colors are being used, and then customize them to the ones we want. These intermediate cells are just showing that we've added in a package called scales. They have different category schemes, color schemes. This one is of categorical colors. And then we're associating those with regions of the world. What hex codes pop out so that we know what colors are being used, and then we could customize those later to the hex codes we want to use to specify the colors. So feel free to open the code cells. I can do that as well, but we could also just kind of focus on the visualizations. Again, other packages let you look at pairwise relationships between variables. So for this one in the upper right-hand corner, it's doing the linear correlation. Along the main diagonal, it's looking at the distribution of each individual variable. So the corruption index is skewed to the right. HDI looks like there might be 2 humps-ish, and neither one is normally distributed. And then you can look at the pairwise scatter plot in the lower left-hand corner. And you can throw a linear regression line on top. And this is one of many examples where we'll see, if you just run straight linear regression, to your eye, when you look at it over the variables, you can see that it doesn't look like it makes much sense. So you want to adjust your modeling strategy to incorporate what you can see in the data. This is all exploratory viz. One of our main variables is going to be the corruption index. Let's just kind of get a better sense of what it looks like. You can see it's skew. Many low values. Remember, 10 is good, less corrupt. And so there's a lot of smaller values leading up to less corruption. And then you can just do a normal overlay to see if it looks like it's normally distributed or not. When you see that the variable in raw form might cause issues, might be skewed. Maybe you want to do a transformation on that variable before you toss it into your model. And so looking at, okay, what if I log transform the corruption index? It looked like it had a right-hand tail. Taking the log of it's going to pull that right-hand tail in. Maybe it'll make it more distributed, normally distributed. And so getting a sense of that visually. So you've got your histogram, got the overlay, can kind of get a sense of whether you'd rather put log of CPI in your model instead of it in its raw form. We'll play with this a lot throughout the other examples, but how many people are familiar with the ladder of powers and using that to test different transformations? It's a fun thing where you're looking at the exponent, the power that you apply the data to. So in raw form, the exponent is 1, you just have your raw data. You could start squaring the data, cubing the data, doing it to the 4th, and if it has a long left-hand tail, it's going to yank that in. And then otherwise, if you start doing a power less than 1 by halves, take the square root, take the log, it's going to yank in the right-hand tail and transform it. So you have this, you can create visuals that are just looking at the ladder of powers across a nice distribution for your variable and see which one yanks it into most normal distribution form. This one, I might even jump into the code on this one because I just love this from a book called Regression with Graphics by Hamilton. I think it's from the early 90s, and it is a phenomenal book. I think all of his code might have been in Stata or some other language, but he uses visuals throughout the entire book to talk about how to use them for pre-processing data for analysis, testing your model and your analysis, and then communicating later. It's just a phenomenal thin book that's, upon rereading and rereading and rereading, is fantastic. And one of the sets of 4 plots that he does in the introductory chapters is looking at these distributions in different types of plots for each variable at a time so that you really understand what they are. And so he's in the text looking at the distribution of water use, and it is similarly skewed to the right, where there's a lot of people that just use a moderate amount of water, and then there's a lot of high water users. And he wants to do some analysis of a program that is meant to reduce water use among everyone to see if it's effective. And so the distribution, the plots are very, very similar to his water distribution. So a histogram of corruption, a lot of low values where that's not the greatest values, and then going up to 10, that's less corruption. You can kind of use the box plot to see if there's skew. The diamond is the mean, and the horizontal bar is the median, so you can kind of see if the mean is greater than the median, then there's skew. And then symmetry and quantile normal plots, is it normally distributed? Is there symmetry in the distribution or not? So all of these are visual cues that there's skew in the distribution. And maybe you want to do a transformation before incorporating it into the analysis. Yeah. Sorry about that. Oh, this is just doing it for once you've logged the data, does it look different? You can kind of get a sense of whether it looks less skewed than in the previous one. So then we get back to the layered grammar of graphics that we had in the presentation, where let's create the plot and just start adding layers and look at our data, try to get a sense. Remember, we're going for that final visual at the end. Within ggplot, you pass in your data set, and then you can pass in any set of aesthetics that you want to display or modify any of the point marks. And so like we talked about positioning along the X and Y axes, we want to say, let's put human development index on the Y, and let's put corruption on the X axis. And so it resembles that final graphic where we have a little scatter of points that looks curved, and then we add points to make them circles. So we're just going to add it up layer by layer. Man, sorry for the skipping. So we create the plotting space in G1, we add our points, and then just maybe initially we want to see if I just throw a regression between the two, what does that look like? So you can add a geom smooth layer, and there's flexibility in that layer, whether it's linear or curved, and so we'll force it to be method LM to be linear, just to see that it doesn't fit the data very well. And so maybe we want to do a transformation. And if your code is able to run and you want to take SC equals false off, then you can see that it does some bootstrapping to see what the scatter of lines would look like, given the variability in the parameters of the regression line, the alpha and beta. So you get a little ribbon around the line to show what it could be. So just adding it up layer by layer. And so here's where we start to think about doing a transformation of the data, or how we're going to transform it just for the regression overlay. And so in this one, instead of using the corruption index in its raw form that we started with, let's take the log of it. Like we saw, oh, it looks very curved. Let's pull in the tail and use the log of it on the x-axis. So this looks less curved. It looks more like a cluster of points that we could fit a line through. That's the type of model that they put in the Economist article. So we're going to, when we plot it, we'll plot the data in its raw form, looks all curved, but in the modeling, we'll use the log to get the curvature in the regression line. So now, I mean, we could still have a discussion of whether we should still add even more curvature in this plot, but we've taken a log of one of the variables, and so now we're trying to fit the line through the relationship between the log of corruption and human development index. And this one, when we transform the corruption index data back into its regular form, this line will turn into a curve, and it'll show up in the Economist article. Try to show everything. I wanted to show the code where we're adding labeling on the X and Y axes and a title, and just kind of getting across that even this exploratory analysis for ourselves, it can be really, really useful. In the previous plots where I had HDI and log CPI, when I was putting this together, I would go away for a day or two, come back to the notebook, and I truly would forget the CPI was corruption and not inflation. So like this final version, even for yourself, of properly labeling the X and Y axes and giving yourself the units or the way in which to interpret it, it just is phenomenal, even for yourself when you come back to analysis after a couple days. And so the other thing that we did, going back to the code, is within the smooth line, what's nice about this layering is you can see that the data points are in their level form. Up in G1, we just used HDI and CPI. They're in their level form. We've got that curvature in the points. They're all leveled. But within the modeling for GM smooth, the regression model we're fitting is the outcome variable HDI on the log of CPI. You can see log X in there. And so the nice thing is you leave the data in its level form, you see it as it is in a scatter plot, but then you can add curvature to the regression line through the model in GM Smooth. And all of these are very similar to things that you could do with code in Python or other languages that supply these capabilities for regression modeling. But we haven't even done any modeling with Bayesian software yet. This is just all with plotting library, ggplot. And you can already kind of recreate the plot that was shown in the article. Okay, so that was all the intro to just kind of getting a sense of the data, doing some initial plotting, seeing if that's how we want to model it, and then we want to get into modeling it in a Bayesian framework. So we talk about priors. We have this intercept and slope for a regression line, the A and the B, the two weights, however you think about it. I think about intercept and slope. And these are the two parameters we're estimating to get this curve. And we want to take a look at what are reasonable values for these before seeing the data, before applying the data. We need priors on both of them. So the two blocks of code right above are just helpful explanatory for before seeing any data, if we use a certain distribution for the intercept, A, and a certain distribution for the slope, B, and the common one is allowing beta to be centered on 0 and have a standard deviation of 1. What do the lines look like ahead of time before we even see the data? So these are the lines that we would produce for the outcome. And you can see that they're just way too variable. The HDI variable only varies from 0 to 1. The Human Development Index, the least value is 0, and the highest value is 1. And these lines are just extremely variable or flexible for positive relationships between HDI and corruption, negative relationships between corruption and HDI. You have some domain knowledge expertise you can input into the prior to make it a little more reasonable ahead of time. Not gonna hit over. So instead of having standard deviations that are so flexible and let these lines vary tremendously, let's say we know something about the relationship between corruption and human development and make them less flexible. So we just reduce the variability of the two, and it's similar to the example that we saw in the presentation before the break. Our variables, y is only going to vary between 0 and 1, and these lines that we have before seeing the data are much more reasonable. They can still be extreme positive or negative relationships between the two variables, but they're constrained to the outcome space for the most part, and not ridiculous. Yeah?
What was adjusted in the code to?
Totally, the standard deviations of alpha and beta. Good call out. Let me show the wild one. So for alpha, we're letting where that line is vary by 0.2. And for beta, we're letting the standard deviation vary by 1 for the slope variability. And then in the second set, we've constrained the beta to only vary by 0.1. So 2 standard deviations out would be 0.2. And so that slope can go up by 0.2, down by 0.2. It's still flexible, but the outcome only varies between 0 and 1. So we don't want lines that have ridiculous slopes, variability. So that was all just thinking, oh yeah.
Sorry, going back to the
Totally.
question as well. Say the slope can now be 0.2, yes, that's roughly given. How do you put it to 0.2? You get a thing that is smaller than 1, right? But why not 0.15? Does it matter, or how do you put the 0.2?
Absolutely, no. To your point, this is like visual inspection given your domain knowledge, scientific knowledge, to say, I want the slope for the relationship between corruption and human development to be able to vary over the full space, to not inject too much influence on it, but to just take a look at, okay, if I assume that the relationship varies this much, what types of lines are possible? And the other one is just too explosive in both directions. And this one is exploring the full space and flexible. So it's qualitative visual inspection of you allowing the slope to vary a certain amount. And in a lot of the texts on this analysis, like the prior is use judgment. And in the end, you wouldn't want the prior that you used to influence the results. So you want to check that over a broad swath of possible values, you informed it with your data, it came up with this final result, and it was not really influenced by the prior. And so this isn't quantitative, it's just qualitative visual inspection to get lines that are reasonable, and hopefully they get swamped by the data. And you could check that after the fact.
That was what you see here as well. It's not that clear on the screen, but more on the computer. That a lot of lines actually go quite far outside of those 2-to-1 boundaries.
Yeah.
So would you want to make it even smaller than that, or?
You absolutely could, but to your point, like if at the end, if you run the regression that we're about to run and you tried 0.15, 0.2, and 0.25, and that influenced the final distribution for the alpha and the beta, you'd want to convey that to people that the prior had a strong influence on it. Like you and I could make this 0.01 and say, we don't expect there to be much relationship, it should be 0. And then that would probably really influence the outcome. And we'd want to report that we were really too constraining. And so this is a situation where, to your point, 0.15 is probably, if we run it, probably very similar. And the data should swamp it, and you'd get the results based on mainly the data. But this is just qualitative, and feel free to try a set of reasonable values. Yeah. I think I like, again, going back to one of the texts, Statistical Rethinking, the author is like, there isn't a right answer to that right now. It is use professional judgment and communicate to others whether it influenced the final results or not. So it's to your judgment. So we finally want to get to the Bayesian part of this whole piece and just do the modeling in that framework. And so one of the things you can do with regression analyses to try to have a better sense of what priors to put on the variables and just make your models way more interpretable, one thing you can do is center your variables. And so this section up above, we're creating CPI_C. That's just all of the corruption values, subtracting out the mean of CPI from them. And the really nice thing about that is then when you're interpreting your model, you're interpreting the results relative to average corruption. Because there weren't any corruption values that were 0. So if you leave it in its normal form, what you're trying to compare to is when CPI is 0, and there isn't a 0 So it's more reasonable to compare to some representative value that you want to compare against, thinking about our comparisons again. So a really nice thing to do is just compare to averages. And so at average CPI, what is the influence on CPI versus slope, versus human development? So there are just a variety of R and Python packages that allow you to do this type of regression modeling. This is just one package, BRMS, but if you're familiar with RStan or RStanArm, or within Python, PyMC, they all look very similar and do similar things. So in the function up above, we pass in the data set. Depending on whether we're trying to do linear regression, logistic regression, Poisson regression, then you put some information in about the family. Linear regression is Gaussian, that's for normal. It'd be Poisson if you're doing Poisson, binomial if you're doing logistic. We'll see that in the next tutorial. You don't have to specify priors. All of these packages will give you really good default priors. Based on the data you put in, they do some very generic pre-processing and use that to inform the priors. I mean, I'm putting this in to show you how you could put in priors that you want. Like we wanted to specify that the beta was 0.1 or 0.2 there. But you can leave the whole block of prior code out. The model will run and use very sensible default wide priors for all of them. Similarly, chains and cores, there's defaults. So this is just to make sure that the plots down below have 4 lines on them for us to compare, but it'll have pleasant defaults. Really all you need are the data and the formula. So we're just regressing HDI on CPI centered. When you specify the model, it's going to compile, and then you can print what it looks like. And it looks like for this model, the intercept is 0.66 and the slope is 0.06. Again, what we talked about in the presentation was don't interpret that yet. Let's make sure that our MCMC worked well and like check a bunch of things before we really interpret it. But by printing the object you just created, you get the output. So it did a bunch of sampling for each of those parameters, alpha and beta. Let's pull those out. Posterior samples in this packages yanks them out. And I think by default, you might get 4,000. So for each of your parameters, it's going to grab 4,000 values. And what's really nice is it's kind of like new data that you can analyze in any way you'd like. You know? So if you need to summarize how did they get the 0.66 for the alpha, it's going to be that B center intercept, the mean of it. So you get a new data set that you can summarize in any way that you need. This is just looking at the data set to make sure we understand what it is, but then we can start visualizing it. So for each of the different variables, I'm just going to focus on the intercept and the slope and then the overall sigma. Do they look like big hairy caterpillars? It looks like MCMC ran well. There's good mixing of parameter values across all of the 4 chains. This is another package Bayes plot that has MCMC trace and a bunch of other functions for analyzing the MCMC sampling and providing visuals of your parameters after you've analyzed the data. So previously was the trace plots. These are the trank plots. We just want to make sure that all of the lines seem to be overlapping and having similar ranks across all of the chains. So it looks like good mixing for all of these. In lots of these texts, the statistical rethinking and the regression and other stories and Bayesian analysis, they all have examples of plots that do not look good. And so you'll see they just have systematic behavior there that looks like the mixing was not good. So then we talked about, one thing you might be interested in is which of the variables observations were most influential. Is it mostly that lots of the scatter is here, but there's one observation way off in the corner that's pulling the regression line over because of where it is and how strongly abnormal it is? It's good to know that. So a way of calculating this information is leave one out cross-validation. There's a package for it in R that lets you do this leave one out cross-validation. And what's really nice about it is it also enables you to do model comparison. So we'll see it return at the end for calculating statistics for each of our models and being able to compare their predictive performance. So these cells say just print the output for the value of it and then add those to the model object that we're collecting. So we calculate a model, let's just add all of these variables to it. And then two of the statistics we calculated are Pareto K and weighted average information criteria. And they're just two different values for evaluating predictive performance. Pareto K values greater than 0.5 are problematic. And so you can always put a reference line at 0.5 and see whether any of the values were greater than that for Pareto K. Here, they're not. And then information criteria, you can just see if there are extreme values in that space that has more to do with information and deviance in the model. And so I just called out in a visual form, kind of going off some of the examples we showed in the presentation. Don't care about these. They're all kind of clumped together. These seem to be outliers, extreme. Let's label them or color them differently, or then let's go look in the data and see why they're different. What region are they a part of? Do we need to build that into the model? I'm not going to do that here because we're just trying to create the economist data set, but like label them and see what's going on with those variables. They're different. These built-in packages have lots of opportunities to print residual plots. I won't spend too much time on this one, but with any residual plot, you're just hoping for a cluster of points and no systematic behavior. This one looks like a cluster of points. It doesn't look like there's a big U shape or scattering of heteroscedasticity. The other nice thing about these, if you step through the code, is remember that the results of our Bayesian modeling is a bunch of sampling. So instead of getting a single value back from the model, for each of our parameters, we got 4,000 values back. And dealing with those and aggregating over them can just be a little more management overhead. And so looking at some of the roll-up statistics or functions you can use to handle the data, I just want to remind you, like, add residual draws to the model object B1 is just a handy way to calculate the residuals for each of those observations. And then median QI is being able to calculate a statistic that does aggregate over all of those posterior samples. So, you know, if you use LM in R and you just get two numbers back for alpha and beta, a number for the intercept and a number for the beta, that it's easy to just handle those two numbers. They're the most likely values. Here we have a bunch of samples to deal with, and it's just a little more data management to calculate the same summary statistics. How well does our model predict data? Or I think this section is actually, you want to calculate the residuals yourself. You know, how would I do that? You can pass the model object into predict, get some predicted values. They're going to give you the estimate, its standard error, and some quantiles. And then the residuals are literally just the observed minus the predicted. But this is calculating it by hand, just to be able to do that. And then creating a residual versus predicted plot. Just, again, this one does show some narrowing of systematic behavior, the narrowing of the variance of the residuals over the predicted value space. So we'd want to look into that. But just a standard plot, and you want them to be a scatter of lines around 0. And so putting in a reference line is really visually helpful. So this is just all of the exploratory visualization we're doing during the modeling. So this was one of those plots that we stopped on in the presentation to say, we've created this model. It is meant to predict HDI, Human Development Index values. We have a distribution of the HDI values that we passed into the model, the actual ones. Now our model can produce new ones. How similar do they look? So the dark black line or dark blue line is the actual HDI, Human Development Index values from our data. And that's their distribution. I think we kind of said when we created the visualization early on, it was kind of two-humped. And then our model can predict, I think up above, I created 500 of these, and we just pull out 50 lines of new predicted HDI values and see how similar they look. So in this case, it's not the best fit because of that second hump, but it's not extremely different. They're not skewed relative to this one. So visually, it's kind of similar, but not perfect. There's different ways to explore the similarity. Those were overlays of those density diagrams, but you could also do histograms. So this is just to show you can, this is the histogram of the original HDI data. So that's the histogram of HDI. And here's the histograms created from your model. And you just want to look at visually, do they seem similar, or very, very different? Again, they have some great examples in the tutorials online within these packages that show, and here's what systematically different would look like, and they're just radically different from the original data. And you could really get a visual sense of, my original data was normally distributed, and what I produced is radically skewed, and you'd want to know that your model is not working properly yet. And finally, we come back to, okay, I just want the number for my A and my B. I just want my intercept and my slope values. How can I roll those up and get my estimates for them to summarize? And so you can just do posterior summary. When you display that, remember we got a bunch of columns. And so the first three are the intercept, the slope, and the sigma value. And then you can just say round those, please. And it'll give you the estimates. And we get back to 0.66 and then 0.06 that we got up above. This is a different way to do it, and just display the results with medians instead of means. So different authors focus on, so many people are so focused on doing the 95% confidence interval that we're trying to get away from that. So by calculating statistics yourself, you can choose a different interval. Those authors often do 89% intervals or 99% intervals to say all the values are in here, just to get people away from using the mindless 95% intervals that are misinterpreted every day. In Bayesian regression, you're not getting a single maxent value back. You're getting a distribution for each of your parameters. So these are the actual results. The distribution of slope variables and intercept variables, the most likely values are in this distribution. That's what your posterior is actually showing. So these are correlated with one another, but showing one at a time. You get these visuals for it. Another way of showing variability in your alpha and your beta is just doing an alpha and beta plot, showing the uncertainty in each of those values. So then we finally come down to, let's start making our way towards creating that economist plot. We plot our regular data. We have some descriptive labels so we know what they represent, and then let's layer in the linear regression line. Where this is different from, I wanted to call it out, where this is different from the previous versions in our early EDA is that the slope and the intercept are coming from our model object. So instead of using geom smooth and just having the plotting library create a line for us, we're using geom AB line to create a straight line. And for that AB line, it needs intercept and slope, and those are coming from our model object. So that's how things are changing now, is we're starting to use results from our model for the plotting. And so the first one was just straight up linear regression. Now let's actually do the modeling with the log of CPI so that we can create the regression curve that's actually shown in the paper. So I'll go through this way faster so we don't dwell on it. But you can see that instead of regressing on CPI in the equation, we're regressing on log CPI. We get all of our hairy caterpillars looking for outliers with those two measures of deviance, looking at the residuals. And I mean, this is the final thing. So for the model data frame, we have the log of CPI, and we have our predicted Y values, and we can use that to produce the line we're going to display. So we pass in the original data, CPI and HDI, just in their level form. That produces that scatter plots that's curved. And then this is just for us to show the similarity between the line that ggplot creates for us, geom smooth, and we specify its formula, outcome, and log x. So that'll produce the line that we see in the Economist article with zero modeling. We get that line just from plotting. But we're trying to do modeling and then be able to do other things with it too. So we've produced this model that'll also produce that curve, and we're going to show that with geom line. So I'm only including both to show that they produce the same line, but that's for us. When you do this, you'll just use geom line and show the line with your modeled model. Yeah?
Do you know if geom smooth does some sort of MLE in the backend, or can you specify like using like a Bayesian method within geom?
I don't know a good answer to that. I know that the flexibility of what you can supply as that little formula is limited. I don't believe they have Bayesian modeling in that formula, but something like supplying a square root instead of log is something that might be possible. We could absolutely, if we have a little time at the end, we could just throw up the geom smooth docs and see what they say is valid formula code. So anyway, that's, geom smooth is just ggplot giving us a curved line, but what we really want to use is geom line. We're passing in our data that we produced from our predictive model, and then we're passing in the exponentiated x values. That's that transformation from we predicted on the log scale, let's exponentiate to get it back to curvature, and then pass that in as the log model line. And then we just have all of our labeling down below. So again, we just wanted to show the two curved lines. The EXP line, I think, is just coming straight from ggplot, and the dotted line is us based on our model parameters. We were talking about how we could use LU, leave one out, cross-validation, to test the predictive performance of these two different types of models. And so the LU package lets you do comparison on different measures of their predictive performance or their error. So one version is WAIC, and so you can see the output of the results of the comparison of the two models. The first one was linear, the second one was curved, and the package always lists the most predictive model first, and then all of the other ones are deviations from or differences from. So B2, the model that allows for curvature, is the most predictive, and then the difference in all of these statistics are shown in the level line for B1. Again, these are all tables. It's just so much more helpful to see images and visuals. So let's just create a plot and be able to show deviance is a bad thing. And so we want smaller numbers of deviance. Try to put that in the title, that smaller values are better. And so if you have multiple models, this is only these two for this, but if you had multiple, you could stack them and see if any are statistically different from the other ones on their predictive performance. Okay, all of that was your exploration phase and coming to the key insight that you want to convey to others, and that person who wanted to convey it to everybody through the Economist article. And so they've come to the point of the plots that they created for themselves, and now let's transform it and customize it and make it publishable. So initially we add the color for each region, and this is what you get with the defaults, just rainbow colors. You can tell the things apart, but it's eye-jarring. We're starting to get closer to the article. They've made the size of the circles larger, filled them with whites, made the stroke width a little thicker for the bands on each of the circles. We haven't changed the color set yet. And they have added in with geom smooth the regression line, curve regression line beneath the points. That's one they point out in the tutorials, is like they allow the points to sit on top of the regression line to push it to the background. And you can do that with the ordering in which you put the lines of code, which one sits on top of which. Then we could say that there are some points that we want to name, and there's a further set of points that we want lines associated with. So just put each of those in arrays or lists of interest, and then we'll be able to use code to draw text or lines to those points. Available in a bunch of different packages, but things like adding text, but making the text repel and not overlap with the points that they're referring to. So the text repel allows you to add the text to different points and then just specify how far away they should be or how close, and you can customize that. So for that first subset, we're using the country is in the points 1 to add the text for all of the countries that we want labeled with text. And then for the second call to it, we're at points 2. It adds lines. When you add the box padding with lines, then it'll draw lines to each of those. So again, we haven't changed the color scheme yet to be like the article, but now we have all of the countries labeled that are labeled in the article, and we have lines to the countries that have lines to them. We have the curved regression line. Maybe we can just show the code on this one. We're switching the color schemes. And so that's where we talked about earlier, where you can use packages to see which color schemes were used, and then find a way to figure out what colors you want to use. For this article, you're trying to match the colors that were printed in the article. You can find those through any color picker. And then those are region colors 1. And somewhere in here down for scale the colors the way I'd like them scaled is passing in the region colors to each of the values, and then they get customized color scheme. We're getting close. The color scheme is like the article, the line. Oh, you know what's not showing up? If you're staring at it on your laptop, there's a huge gray grid with a lot of lines, and the legend is still over on the right-hand side. The grid is not showing up here, but what we want to do is start getting rid of the grid and customizing the grid and move the legend as well. So we moved the legend up to the top and made it horizontal to be like the article. And then we customized the grid, which now we can see. And so it was a dense matrix, and now we've gotten rid of a lot of the minor lines and just accentuated some of the horizontal ones, just like in the article. To be really consistent with the article, we're chopping off the y-axis at point 2 instead of letting it go all the way to 0. I just want to call that out as something I would not normally do, but this is to replicate something that's shown in the article. And so we're customizing that in the y-axis scaling and saying start it at point 2. That was the end. So for this first one, that was getting really close to the article version. Let me just go back to the article version. So it had those dark horizontal lines, had the curvature and the axis at the top and the labels on either side. If we go back to ours, because it's plotted in the cell, it doesn't have the same aspect ratio or length and width, but it's very, very, very similar. So before we switch,
Well, it's more clear than this plot than the one in the article because it's more spread out. Actually, if we go back to the one from the notebook. So it looks like it's still quite a bad fit, right? As you mentioned before, because all the African countries are on the, let's say, the left side or the underside of the red line, and then the next one's all above. It looks like there's a big group of countries that are just vertical, and then at some point, like from South Africa, there is a linear. Is that where the hierarchical regression thing comes in? Where you basically fit one almost vertical line, and then the second one for the second part of this?
That's an awesome question. Model this differently, not the way that it's displayed simply for the Economist article. Absolutely, and different ways. You could do it with the hierarchical modeling, but to your point, it could be as simple as saying creating a new indicator variable for countries with CPI between blah and blah, and just build this thing into your model to say, I want a separate intercept and slope for this stuff, and make a different one for those. This one was just to mimic what they did, but to your point of make a better model, absolutely. It doesn't really curve down enough to go through these points at the bottom either, so there could be all sorts of improvements That's a great call out. I love, just to talk about one other example from, again, the Statistical Rethinking book near the end, he does an example where we fit some linear regression that's curved and is the best we can do with just a functional form transformation. And it's exactly like this. It kind of fits and looks pretty good, but his example is something where with domain knowledge, I think it's the amount of tools in a population given population size and some other factors. And scientifically, we know if the number of people in an area is 0, the number of tools there is 0. And so it's like that line should curve through 0, 0. And so he goes through the rest of the chapter saying, with scientific knowledge, let's make a new model such that 0, 0 is where it's going to go through, and it goes up as population goes up in a curvilinear fashion. Like, it's a great example to your point of we could do better. Yeah. How are people feeling? Do they want logistic regression? Do they want the one with the countries at the end? I think with a half an hour left, even 25 minutes, we'll just kind of quickly run through one more, and then we can talk about them in the final 5 minutes. Logistic, just for like difference, or? So for the second one, it's coming from this text, Regression and Other Stories. That's what the cover looks like if you're ever looking for it. And then all of their code is available online for all of the chapters in this examples section. So you can just step through, and they have examples that are printed out with explanatory text so you understand what's going on, but also the code blocks to see what's going on. So just you can get all of the data sets and all of their explanations of why they model it. And the authors are a mix of Bayesian and ggplot fans, so they often have examples in both. So it's really easy if you're coming from Bayesian or ggplot to see examples in both. So one of the chapters on logistic regression is talking about, do people move to a new well depending on the toxicity within their nearest well and how far they'd have to travel to get clean water. And so it comes from this paper that I'm linking to here, and then they incorporate it into the text. So it looked like mine finally finished, so I can run the cells, but we will just look at it. They called their data set wells. So the outcome variable is binary, 0, 1. The family did switch or did not switch to a new well. The arsenic levels over 0.5 are starting to become harmful. And so these ones that are 2.9 are just, you should really think about changing your water source. Distance to the nearest clean well. And we'll look at a data transformation where the next column over is in 100 meters. Because otherwise the data was in meters, and it was like the variable was relative to moving this far and this far, 1 meter at a time. And like it makes more sense to have to travel, say, hundreds of meters. So it's an easy data transformation to make it more interpretable. The first few cells, just all that exploratory data viz. Because we'd use them in transformations down below, like what are the mean values for did switch and didn't? You know, distance is 0.4 and 0.5. So people that were closer switched, and arsenic levels are higher for people that switched, which, you know, is what we're going to analyze in the thing, but you would kind of think higher arsenic, more likely to switch, greater distance, less likely to switch.
Is there a variable to say which well they switched to, what arsenic level is in the newer well?
Say it again.
Is there, was there a data point that, the column that actually showed the arsenic levels of the well that they switched to?
Not as far as I know. That's a great question. Yeah, no. I think they just use arsenic level in the well that they have a decision to decide about. But that would be phenomenal to do that connection and see the improvement in quality given the switch. So just, again, creating visuals is so nice, a reminder that like our outcome variable is just zeros and ones. Just good visual reminder that you're not seeing a scatter plot and things like that. And then there's a relationship between distance in 100 meter units and arsenic. Just seeing the relative relationship between each of the variables. And then there's an emphasis on understanding, again, the distance. Initially, it's in units, so just trying to see whether we should transform that variable to 100 meter units. We do. to make it more interpretable, and whether it's skewed and needs to be transformed in any way. So this is the raw level in 100-meter units. So most people are less than 100 meters, but there are some with a long tail. Do we make the variable more normally distributed if we just take the square root of it? So I think, or take the log. So this is an example of exploring the ladder of powers to see if maybe your transformation is too strong. So in the square root transform, that looks pretty good. It looks like it's fitting the normal pretty well. When we take the log, it looks like we've introduced a left-hand tail where there used to be a right-hand tail, so it was like too strong. So you could also use some automatic transformation finder like Boxcox to find the right exponent. But 0.5, pretty good. Log, too strong. Again, I like this block of code where we create these 4 different plots and look at the relative distribution. And this is one variable at a time, but looking at its distribution in 4 different ways, just to really understand your data. And what it looks like when you take a transform. And then this is the scatter plot that we're generating, similar to the one we did for human development and corruption. This time our outcome variable is only 0s and 1s, and so we can introduce another visualization technique for kind of scattering those points a little bit to make it more visually understandable. So let's use a jitter, just to scoot the points away so they're not laying on top of one another. And so we just introduce a little bit of scatter so that we can see the relative density of points given distance and the relative switch. That's what it looks like when we take the log of distance. But we talked about how that was a little strong, so we're not going to do that. But just this was part of exploratory analysis where you're trying to figure out what's going on. To your question about flexibility in the geom smooth, there are different transformations, like they can do logistic regression and introduce the curve for logistic. And so we haven't done any modeling yet, we're just doing the visualization. But they have geom smooth, and I want to run a logistic regression. And it looks like since you do method GLM, they could probably do lines for Poisson and negative binomial and like any of the exponential family. And so we just introduce, and without even doing any modeling, visually, this is what the data looks like as the decrease in the probability of switching given distance from the clean well. And so it looks like even when you're really close to the clean well, the probability of switching is around 60%. And then the probability of switching really decreases as the distance to the clean well increases. Sorry, and this is just the final version of adding nice labeling on X and Y so you remember for yourself what the plot is displaying. So we're doing logistic regression. We need to do some prior predictive simulation on the alpha and the beta for the curve we're going to create, the line. This is how the modeling code changes a little bit for doing logistic instead of linear. The family is no longer Gaussian, it's binomial. And there's different ways to supply the left-hand side of the curve, the switch given trials. I'm doing it this way because that's flexible for you if you want to do number of counts versus exposure. So if you're starting to do Poisson or negative binomial and you want to say, I got another classic example that they have for the difference between Poisson and negative binomial is they're trying to look at the number of rats they find in this apartment complex given the number of days they look for them. And so this specification is flexible so that if your outcome variable is count of rats found, then instead of trials 1, it could be trials of exposure variable, number of days looking. So this one's flexible, but for this binomial regression, logistic regression, all of them are going to be trials 1. So put together some plotting code. And I just love this plot. This one is also from statistical rethinking because he's hammering home the point that the prior distribution on the likelihood, you're thinking the probability of switching varies between 0 and 1. And so if you're unsure, then the curvature of your expectation should be kind of flat in that area, or maybe just a gentle hill between 0.5 and 0. So the uniform distribution shown in blue is where we're making the prior distribution more restrictive. If you make the prior distribution of the likelihood of switching really flexible, in the outcome space of the probability of switching, you get this really peaked outcome if it's either they're not going to switch or they're going to switch. And before you see the data, assuming that it's either 0 or 1 is a bad assumption. You want the one that's uncertain and like entertaining lots of values between 0 and 1. So in the code up above, the first block will create the red section, and I think the standard deviation in that is the mindless 10, and then making it less flexible, smaller standard deviation down to 1.5 constrains it, and your prior distribution becomes way more reasonable. So then we pass in our Wells data, we create a binomial regression for a logistic regression, and we're regressing the probability of switching, whether or not they switched 0, 1, on distance in 100-meter units. And that's it. And you don't need the prior call, it's just there to show you how you could customize the prior. When you wrap it in print, you get to see the intercept and the slope. You get to see, remember we saw visually that it looked like when distance was 0, when distance was 0, the probability of switching was around 0.6. We get that 0.6 back. And then it looks like the downward slope in that line was around negative 0.6. But again, we want to quickly do our MC-MC diagnostics. Does all the sampling look irregular and mixed well? Yes. Do the Trank plots look for different ranks of each of the outcomes look overlapping and equally erratic? Yes. For this one, we can also look at Pareto K and weighted average information criteria. Nothing's above 0.5. The tool itself, if you get observations that have a Pareto K of greater than 0.5, it'll tell you that, and for each one of those, it'll programmatically rerun some estimation of the modeling, excluding those to see their outlierness, their influence, and give you some diagnostics about the troublesome things. So in all of these, the observations aren't problematic, but if they are, it provides you with a lot of tools and information for correcting them. So just getting a sense of whether, now that we've done the model, can it reproduce the distribution that we saw with our original data? So the deep black line is the actual density curve for our outcome variable, which is just 0s and 1s. And our model produces lines that are very much like that. So this looks really good. It can produce the distribution of 0 and 1s that we see in the data. Seeing it with histograms instead of density plots looks very similar. And then from our model, we can just summarize the data and get the 0.6 and the negative 0.6 back. You can do it instead of getting the maximum entropy expectation values, you can just get any other summary statistics like medians or quartile ranges, anything. In Bayesian regression, we're really interested in these distributions. Instead of summarizing them with the mean value, we can print these in the paper and say the parameter value for the intercept is between 0.4 and 0.8, and the 99% confidence interval for it is between 0.41 and 0.79, something like that, if you really need to summarize it. But the information to share with everybody is the full distribution. And if we do any prediction or any analysis based on the model, it will use the full distribution of values for each of these parameters to inform the predictions, not just some summary statistic from it. This was an example where I didn't do any transformation of the variable to make them uncorrelated, so they're negatively correlated. Higher intercept values are associated with lower slopes, and smaller intercept values are associated with higher slopes. Again, just the same trick of producing the output from the model and putting it into a data frame so that ggplot accepts it. So this little pre-processing step is just making sure that we can pass that in as a data frame to ggplot. So it's kind of language specific. But we want to get, given the distance, the predicted probability of switching, and that's going to be our line that we trace out over the original data. And then again, I think I'm just showing the two options of Geom Smooth is just doing it with the plotting library. You didn't even have to do any modeling and you get a curve, but you haven't modeled the relationship between them. And Geom Line is based on our data. And so that's reproducible and you could use the model for prediction of other variables. But you can see the final outcome is they produce the same line. So we have our distance in 100 meters. We're jittering the points a little bit so we can see the relative density at different values on zeros and ones, and then the prediction line. As a second example, we talked about that was only using distance. Maybe you also want to use arsenic level. And as arsenic level increases, we'd expect the probability of somebody moving to increase. So let's see if that gets incorporated into the model. So now we'll have two models to compare. I know we'll look at the MC-MC diagnostics, but just looking at, the intercept is 0, as distance goes up, because it's a negative slope, the probability of switching goes down, and then arsenic level has a positive increase on the probability of switching. So the trace plots, residual plots. And so in the code up above, now what's really nice is we can start creating separate lines, like with our model to say the relationship in the data is between distance from a safe well and the probability of switching. And what does that line look like based on the arsenic level? And so we can't test for this 2D visualization all of the arsenic levels, but you could create several reasonable ones. And so at 0.5, the arsenic level is becoming unsafe. And so that's a good baseline to compare against. And then say, what if it's doubled? What if the arsenic level is 1 and really high? Is the probability of switching higher? Hopefully. Or is it lower? So against the orange baseline, if arsenic level is higher, for any given distance from a safe well, the probability of switching is higher. It's on top. So you could do that with a few levels of arsenic and get some lines to tell a story about the way in which arsenic and distance influence probability of switching. When we compare these models with leave one out cross-validation, here's an example where it's easy to see. The confidence intervals aren't overlapping, so you can see the second model that incorporates arsenic is way more predictive of probability of switching than the previous one. So we'd want to go with it. And then finally, we had all those plots for our understanding. Let's clean them up a little bit and make them presentable to others for publication or for communicating to other people. So we have our first version. It's a pretty good starting point. We have our title, we have our axis labels, we have the original data, and then we have two comparison lines, so for different arsenic levels. So we can change the theme. It looked like, if you're looking online, different grid line density and shading of the grid space changes. So just trying to mute out all of the unnecessary ink, add much more of a descriptive title of what each of these lines represents, adding a data source down at the bottom. You may have found some of the text harder to read because it was by default smaller, and just literally for publication and for your readers, blow it up, make it larger. And so making everything larger. And there were some minor grid lines that I believe are invisible, but getting rid of those. And so the background is much more clean. And then a little bit more customization. Some of the text was scrunched and close together, and just spacing it out a little bit. And you can show code to just add some spacing between each of the texts, some margin around the blocks of code, and space things out. And then it's kind of ready for publication. So I think this is the final one. Yeah. So that was everything. Just to kind of bring it back really quickly, and then we can just wrap up. Coming back to the presentation, please feel free to go to the GitHub repo. It has this presentation. It has all of the notebooks if you want to revisit the presentation or any of the notebooks. Remember the key points of the presentation were just, there's these two phases of understanding for yourself and then communicating to others. And that second phase, we need to be thoughtful about it to convey the main takeaway, the big idea, and answering so what. Why is it important? Why does it matter? Communicating that really clearly. So that's everything. Yeah, thanks so much. Yeah.
Thank you so much. It's wonderful. How does this change if we try to visualize results from user studies, where we may have the opportunity to collect more data?
I don't think it would at all change it. You would just incorporate that new data, and either, depending on your audience and what you're trying to convey, either you incorporate it and say this is an updated analysis and present results very similar to the ones you presented previously, whatever graphics, with more data, and say that it's updated. Or if your story is changed since, then you could reanalyze with the new data and do visuals that communicate, here's what it was, here's what it is now, and what visuals would communicate that story, if I'm interpreting you correctly. But incorporating more data into the analysis is fantastic.
And then what plots would you advise to put in papers, keeping in mind that we are in a community that's very much into hypothesis testing and p-values? So what kinds of advice do you have for us to maybe change our culture a little, and what kinds of plots? We can't show all of them.
Yeah.
But which ones do you think are essential?
Before going into specific plots, I think just the general idea of you have explored a particular research question to try to figure out something in specific, then the final plot that is the emphasis of the presentation is something that clearly communicates your finding about that thing of interest, is the critical one. If you were looking at did something change between previous study and this one, the plot should clearly communicate the change message of whether there was or was not. And to your point, some of the plots that have to do with the testing of the model and the parameter things, they may not even make it or just put it in the appendix. The thing you want to convey is your message, your finding, your insight. And some of this is just supplementary supporting. The nice thing about putting it into a code file is you could put that in the appendix as a resource and somebody could rerun your thing, and then you don't have to supply any of that. It's just, if you want to see the same exact results, go run the code. But for plot types, it would just really depend on what message you're trying to convey. And then a nice default is push everything to gray and then accentuate what you want to accentuate. Something changed, so accentuate the change line, and then have a title on the steps that says this thing changed by 2 points between 1990 and 2020. Something is, you communicate what should they take away from the picture, and what's shown in the coloring scheme and everything conveys that message. I know that's pretty general, but I don't know the research finding. But to your point of people focused on the hypothesis testing and p-values, that'll take time, and knowing your community culture of how to communicate that to people that are looking for that if they're your reviewers, or I don't know the best way to deal with that because, like you said, it's culture change, and maybe what you do is start communicating both. Showing people the P95s. In all of the output we created here, I could definitely communicate the values that are the ends of a 95% confidence interval, but would choose not to. But you could do that if the reviewer needs to see it. And then later you could say, but the 99% confident is this, and I believe it's between this and this. And that's legitimate in this Bayesian framework, where the curve we're creating isn't a confidence interval. So it's a probability distribution, and we can calculate any stats we want off of that. It's a great question. Yeah. Yes. Yeah. But I see you trying to but how do I communicate to people that want to see a certain thing? maybe you show both, and maybe even emphasize the one they want to see, but have the other available as you try to move people from one to the next. It'll take time. But yeah, showing the, oh yeah, a graphic for the alpha and the beta, showing the full distribution, but in the text or even in the title, it shows the confidence interval, if that's what they're looking for. Could be like a nice compromise. But yeah, we're trying to, in the work that we do at work, it's okay to use different confidence intervals because people are interested in different ones and interested in the question at hand. So it's more in if you can communicate the finding you found and how it answers the question, there's a lot of flexibility in which thing you communicate. Nobody is looking for the p-values and the stars anymore. So it's okay to use other stuff. Cool. Man, thanks so much for coming. I mean, it was a lot of fun talking about this topic with you. I really, really enjoy it. So please keep in touch, or just hope you have a great time at the conference too. I'll see everybody for the other ones between 2 and 5, I guess. Have a good one.